Say a particle is locked in centripetal motion. The position vector r would be a radius of the circle. The velocity vector would be tangential to the circle. We know from circle properties that the tangent is always perpendicular to the radius at the point of tangency, and this applies here. But why is the result always circular motion? Why is it the case that when the position vector is perpendicular to the velocity vector, the result is necessarily purely circular motion? Let's go through a proof. And this is something that you would typically see in a multivariable calculus course, but I'll try to make it as simple as possible. Let's think of the most generalized two-dimensional position vector r of t. R is written in bold because it describes a vector-valued function, a function that assigns a vector for each value of the independent variable. On paper, you would write it like this, r with an arrow on top. Anyway, the independent variable here is t, which can be thought of as time. Really, it's the variable that is parametrizing this curve, relating the x and y components to one another. The x and y components are, of course, f of t and g of t. I and j, as you may know, are the unit vectors along the x-axis and y-axis respectively. So this is the most general position vector in the two-dimensional plane. Velocity is the derivative of displacement. So the velocity vector can be found by differentiating the position vector. Now, we know that the position vector is always perpendicular to the velocity vector in centripetal motion. So, we know that the dot product of r and v must be 0. So, using this as the basis of our proof, let's see what we get. Doing the dot product, we get f times f prime plus g times g prime equals 0. Now, this reminds us somewhat of the product rule, but it's missing a few terms. Fortunately, the right-hand side is 0, so we have more leeway in terms of multiplying both sides or dividing both sides by a constant. If we multiply both sides by 2, notice that we can spell out the individual terms like this. The first two terms would actually be the derivative of f times f because it would be the product rule in action. F times f prime plus f times f prime. You can think of f and f as two functions, and then it's clear to see how this is an application of the product rule. And the same thing applies for the following two terms. It's the derivative of g times g. So we have the derivative of f times f plus the derivative of g times g equals 0. Now, of course, f times f is f squared and g times g is g squared. Next, we can use the linearity of the derivative to express this sum of derivatives as the derivative of the sum. So now we have the derivative of f squared plus g squared equals 0. If something has a 0 derivative, it means it must be a constant. So f squared plus g squared must be a constant. Let's call it c. But remember that f of t described the x component of the generalized position vector we started with, and g of t described its y component. So replacing f and g by x and y, we get x squared plus y squared equals c. And this is precisely the equation of a circle. So we conclude that the fact that the position vector and velocity vector are always perpendicular, or we would say orthogonal when we're talking about the vectors, necessitates that the result is circular motion.